let us consider one more important chapter that we have, which is mainly dealing with the energy principle as such. But before we could actually start with the energy principle problems, we will have to first of all recall the Newton's laws, and out of that the most important law, that is the second law of motion, which says that force is directly proportional to rate of change of momentum. Now in the impact problems we have considered what is the momentum. Momentum is nothing but the product m into v. So we can write the equation as force is proportional to d by dt of m into v. Now mass is not the entity which is going to change with time unless the problem is using such an entity. So mass is generally constant, and so force will be written as d by dt of mv, which is nothing but m into dv by dt, and dv by dt is the term which we are specifying as the acceleration, that is the rate of change of velocity. Now once we consider rate of change of velocity, that is acceleration, and if the body is acted upon by several forces, then the acceleration of the particle will be in the direction of the resultant force. And resultant force is the concept that we have studied in statics. When there are several forces acting on a particular body, then we can take the summation of their x components as well as summation of their y components, and we can find out the net resultant force as well as the direction of that particular force. Now the acceleration of the body is going to be in the direction of the applied force, that is the resultant force. And so we can write one important principle, that is summation of all the forces acting on the body is nothing but mass into acceleration. Now here again we are not learning anything that is very new as such, but the same thing can be splitted further, because now we can think of the summation of the forces in the x direction will be equal to mass into acceleration in the x direction, that is horizontal direction, and similarly summation of forces in y direction can be considered as mass into acceleration in y direction. So the acceleration is now going to have two components, x component as well as y component. Now these are all the simple terms, the simplest law that we have, Newton's law of motion, which we are going to use over here. And based on this we have got some principle called as D'Alembert's principle, which says that summation of forces minus mass into acceleration of that body is equal to 0. Summation of forces, that is sigma f minus m into a equal to 0, is nothing but the D'Alembert's principle. Of course D'Alembert's principle we can implement it in x direction, and we can say that sigma fx minus m into ax will be equal to 0. Similarly sigma forces in y direction minus m into ay is equal to 0. Once we understand this rate of change of velocity type of concept, that is acceleration, we can go further to discuss another concept in energy, that is the potential energy. The potential energy is nothing but mass into gravitational acceleration into the height. Now actually mg is nothing but the force which is the inertia force. So mg is always acting in the downward direction, and when the body is raised to height h, we will say that the body has gained the potential energy, which is equal to force into the distance travelled. Now the distance travelled is nothing but the height which we are assigning to that particular body, which is h, because that body is assumed to be at height 0 and then it is lifted up to height h. So the work done will be the work done by the weight of that particular body, and therefore work done in this case can be considered as mg into the distance travelled h. In other words, it is called as the potential energy. We also have got the energy in the form of kinetic energy, which we have used in earlier problems of impact, that is 1/2 mass into velocity square, 1/2 mv square is the kinetic energy. Power is the term where we are going to talk about the work done per unit time. Work done per unit time. So it is going to be the force into distance per unit time, and distance per unit time is nothing but velocity. So the power can be calculated as force into the velocity. We have also the principle of what is known as the impulse. Now impulse is going to be a large force applied for a very small time. So it is going to be force which is applied for small time, say T1 to T2. So force into T2 minus T1 can be equated to mass into the difference in the velocities, that is V2 minus V1. Actually the term V2 minus V1 upon T2 minus T1 is equivalent to acceleration. It is change in velocity with respect to change in time. But instead of writing it as m into dv by dt, we are writing it as f is equal to m into dv by dt. Therefore f into dt, I am taking that dt on the left hand side, equal to m into dv. And if we integrate left hand side for time, for t equal to t1 to t equal to t2, and right hand side for velocity from v1 to v2, we can write it as impulse, that is force into t2 minus t1, equal to initial or rather final momentum, that is mass into v2, minus initial momentum, that is mass into v1. So even the impulse can be calculated. Work energy we have already seen, that is force into the distance traveled, and we have also the energy which is stored in the spring. Now energy stored in the spring will depend on the constant of the spring, and as the spring is compressed by distance x, every time the force which that spring can produce, because if you know the constant of the spring terminology, it is nothing but the force required for the change in length, which is going to be a unit length. That is the definition of the constant of the spring. Now when the spring is free, it is not exerting any force on its own. When the spring is compressed by 1 meter, then it is going to exert a force which is equivalent to the spring constant, and it is a linear variation. And so when we talk about the energy that is stored in the spring energy, it is going to have the value which is equal to 1/2 kx square, where x is the compression of that particular spring. Now with all these considerations, we can proceed to some problems or the discussion of some problems which are to be solved in this energy principle. We have applied the energy principle in case of the impact problems, when some ball or the stone is dropped from height h and then it is going to hit the ground. At that time we have been every time using the principle, that is the change in the potential energy is nothing but gain in kinetic energy. We have also used the energy principle in those problems when the object is hitting some block which is resting on the surface, and when the object hits that particular block, that block used to get some velocity. That means it was getting some kinetic energy, and that kinetic energy will be actually dissipated in overcoming the frictional force, and the work will be done against the frictional force. So energy principle is not the principle which is very new to us, because directly or indirectly we have used it in earlier cases. Now consider the case when some block or some body or some vehicle is moving up the inclined plane. Some vehicle is just moving up the inclined plane. We are also given the slope of that particular inclined plane. Hello? Huh? Consider a vehicle which is moving up the inclined plane, and we are also given the slope of that inclined plane, say 1:20 or 1:30. That slope is also specified. We are given that the the particular body starts from rest, so it is going to move up the inclined plane, it starts from rest and is going to attain some velocity in some time. So this information is available. Say we can say that it is going to attain a velocity of 5 meters per second in a time period of 15 seconds. We are required to determine the tractive force of that vehicle. We are required to determine the tractive force of that vehicle if it has got a mass of say 2000 kg and the resistance to the motion, that is the frictional force, is 200 newtons. Now try to understand the problem first of all, and we are also required to understand one more term which is coming into it called as the tractive force. The body is accelerating, it is moving up the inclined plane. Fine. What information do we have? We know that it is starting from rest, so u is 0. We know that it is going to attain a velocity of 5 meters per second. Fine. So final velocity v is known to us. We also know the time taken, and there is a wording saying that it is the constant acceleration which is acting in this particular time. So we can use the equation v is equal to u plus at and we can determine the acceleration. V is 5 meters per second, u is 0. Acceleration is to be found out and the time is given to us as 15 seconds. So it is going to be as simple as saying 5 is equal to a into 15, or a will come out to be 0.333 meters per second square. Once we find out the acceleration, then we are required to go for the D'Alembert's principle, or we will have to consider the body and also consider the forces which are acting on that body. That vehicle, when it starts moving up, there is some external force which is acting on it. We have already gone through the particular phenomena of calculating the acceleration which is going to be along the plane. One consideration. Secondly, as that vehicle is resting on the inclined plane is going to give some reaction. And thirdly, it is the frictional force which is going to oppose this particular motion. The frictional force which is going to oppose this motion. Now the frictional force, its value is given to us as 200 newtons. The value of the frictional force is given to us as 200 newtons. Now as we proceed further, we are required to consider the free body diagram of that block. Again, I am not going to draw that particular block because that happens to be the usual practice when we have considered the topic called as friction in statics. As the weight is acting downward, and if we consider the component of the weight which is perpendicular to the plane, it will come out to be W cos theta. Now W in this case is given to us as 2000 kg, which is the weight of the vehicle. That is the mass of the vehicle. You can multiply by 9.81 and you will get the weight, that is the W factor as such. And cos theta, we are given the slope of that particular plane which is 1:10. So cos theta also can be calculated. Now the tractive force is nothing but the normal reaction, because due to the tractive force the particular vehicle is going to stay on the particular surface as such. So let the tractive force be V. So it will be V, that is the normal reaction, minus the weight component which is perpendicular to the inclined plane, which is W cos theta, will be equal to the acceleration of the vehicle, in the direction which is perpendicular to the plane. Now the vehicle is moving along the plane and the acceleration that we have calculated, that is 0.333, is nothing but the acceleration along the plane. So I am not solving the problem as horizontal or vertical, but I am considering the coordinate system as along the plane and perpendicular to the plane. Now perpendicular to the plane, we have got the component of the reaction which we are indicating as the vertical component, say V, minus the component of the weight which is acting the component of the weight which is acting perpendicular to the plane. So it will be V minus 2000 into 9.81 into cos theta. That will simply come out to be 0, because it is sigma forces in the direction which is perpendicular to the inclined plane. Sigma forces in the direction which is perpendicular to the inclined plane will be equal to mass into acceleration, and the particular body is not going to move perpendicular to the plane, so the acceleration in the direction which is perpendicular to the plane is going to be straight away 0. And so we can find out the vertical reaction. We are going to find out the vertical reaction, which will straight away come out to be 2000 into 9.81 into cos theta. Now once we get this, then we can proceed further. Once we get this, then we can proceed further, and the tractive force will be the force required which is going to push that particular body up the inclined plane. Now again, the factors which will come into picture in this case is when the body is moving up the inclined plane. First of all, it is going to have some component of the weight which is acting downward. This is again we have seen in case of friction, and that component is going to be W sin theta. So that component can be calculated. As the body is going to move up the inclined plane, frictional force also will be acting down the inclined plane. Its value is directly given to us as 200 newtons. And the tractive force will be the force which is required to give the acceleration of 0.333. So we can write the equation in the form saying that sigma forces in the direction which is along the inclined plane, sigma forces in the direction which is along the inclined plane is equal to mass into acceleration. Now the sigma forces, first of all, it is the tractive force which is responsible for moving the vehicle up the inclined plane, minus the frictional force which is acting down the inclined plane, minus 2000 into 9.81 into sin theta, which is again acting down the inclined plane. This will be equal to mass into acceleration, and mass value is 2000 and acceleration is 0.333. So if we substitute everything, then we can determine the tractive force which is required for this particular movement, and we will be through with our job of determining the tractive force. So the problem is solvable provided that we give the proper thinking. If in this case we go for calculating what is known as the normal reaction, as we did in the earlier case, that normal reaction is not going to help us much, because we are directly given the frictional force. That normal reaction would have been very much useful if the problem would have contained something called as the coefficient of friction. Once we complete this particular problem, there could be another problem where we are given the motion of some block. It is stated that some block is now moving down the inclined plane. So it is the slope, and the object is going to move down the inclined plane, and to stop that particular block we are going to use some spring. So as the block comes down and hits the spring, that spring is likely to get compressed. The spring is likely to get compressed, and we are asked to determine as what is the compression in that particular spring. We are asked to determine as what is the compression in that particular spring. Now of course, while stating this particular problem, we are given even the initial position of that particular block with respect to the spring. So the distance along the inclined plane is given to us. The information about the slope is given to us, and the constant of the spring is also known. Now how do we start with the solution? Of course, in the problem statement they are also mentioning what is known as the coefficient of friction. That means there is going to be frictional force which is to be overcome when the block is sliding down. Now as we start solving the problem, it is going to be the loss in potential energy, because the object is going to move down the inclined plane, its height is going to drop, and that loss in potential energy is effectively the speed that object is going to get. So loss in potential energy is nothing but gain in kinetic energy. That is one job. And secondly, while doing this, it is not only the kinetic energy to which this potential energy will be converted, but it is also overcoming the frictional force. Now we will have to find out the frictional force. For that we will require the normal reaction. The problem will be solved in the same manner as we did the problems in case of friction. So find out the normal reaction, find out the frictional force, and we know that how much distance it should travel. So we can very well determine the work done in overcoming the frictional force. We can also find out what is the net displacement in the vertical direction, that is loss in potential energy, that will be effectively getting converted into the kinetic energy. Now when it hits the spring, that kinetic energy which the particular block is possessing, that will be lost and it will be straight away converted into the spring energy, which is 1/2 kx square. So we can calculate the change in the energy. We can calculate the net kinetic energy that the body will be having when it is hitting the spring, that is 1/2 mv square. And that 1/2 mv square is nothing but the potential energy minus the work done in overcoming the frictional force. And then it will be equated to 1/2 kx square. K is given to us, x square is the only unknown, and we can find out the deflection of that particular spring. So energy principle is to be used very thoroughly in this case. Finding the frictional force is going to be one foremost problem which we are required to solve. Finding the frictional force is the only problem that remains with us, and it can be solved in the simplest manner. Sometimes it is stated that, sometimes in the problem statements it is given that the resistive force is some function of velocity. There are problems where some ship is to be modeled and we are given the information that the resistance of the water, because that ship is going to move on that water, though we say it is on that water surface, actually there is a lot of portion which is below the water's level as such, and then it is going to feel the resistance due to the water. Now if that resistance is given to us as say proportional to v square, or to be precise say 2v square, so when the ship is trying to move ahead, there is going to be the opposing force which is the resistance of the water. Now if we are required to model this particular thing, then we can say that the sum of the forces will be equal to mass into acceleration. Sum of the forces will be equal to mass into acceleration. But then here we are seeing only the resistive force, which will be equal to mass into acceleration. So we can say that the force, that is the resistive force which is given to us as say 2v square, will be equal to mass of that ship, which is say known to us, into the acceleration, which we can write it as dv by dt. Now if we are required to actually integrate this particular thing, which is very well possible, because now we have got something like 2v square equal to some mass into dv by dt. We can rewrite this as 2 dt is equal to mass into dv upon v square, and this can be very well integrated, and that integration will be say from time t equal to 0 to some time t. But then at t equal to 0 we should be knowing the velocity, and suppose that velocity is given to us say 2 meters per second, then we can always have a relation, because then I'm on the left hand side I am going to integrate from t equal to 0 time 0 to time equal to t, and on the right hand side that dv upon v square term will be integrated from velocity equal to 2 meters per second to some general velocity say v, and we will get a relation between the time and the velocity. We will get the relation between the time and the velocity. Now we will have to determine in this case as how much is the time taken to attain a particular velocity, or if there is no applied force as such, only due to the resistance, the ship is going to reduce its velocity. So we can always substitute that velocity, the new velocity, which is going to be, say, the velocity of the ship, which was initially 2 meters per second, is dropping down to 1 meter per second in time t. Then we can very well find out the time t in this particular case. Also, that we can go for finding the displacement, because as we have calculated the time, we can very well say that we can determine the displacement when the velocity of the ship drops from 2 meters per second to 1 meter per second, because in that case the acceleration should be simply represented as v into dv by ds, and our job will be rather a simpler one. So the problems can be solved when the formulation of the problem is given to us. The D'Alembert's principle can be used in the simplest form, and we will be solving the problems which are related to the energy principle. Now in this energy principle, though the direct applications we have seen over here, there could be some indirect applications which we have used in case of the impact problems. We have used the same in case of the initial problems, where the displacement of the body is given to us in terms of time. That is, the position of the object is given in terms of x, y and z, where x, y, z or x and y are functions of t. Then from x and y we can find out velocity in x direction, velocity in y direction, and subsequently acceleration in x direction, acceleration in y direction, and we can very well determine the components of the force in x direction and y direction, and we can proceed with the application of D'Alembert's principle. So these are a few problems where the D'Alembert's principle can be used very easily. Even in case of the problems where we have said that the pile is to be dragged inside the earth, over there also the energy principle has been used, and the resistance over there, the problem that we have solved was the constant resistance, but even that resistance can be specified in terms of the velocity or in terms of the acceleration and so on. So the energy principle is the one which should be applied to all the subsequent problems which we are learning in case of dynamics, though the direct application of energy principle will lead to any of the earlier situations which we have discussed, and all of them should be thought of very thoroughly. Consider a few problems which can be solved using energy principle. Say we are given the slope and there is some block which is placed on the horizontal surface and some ball which is at a distance, this angle is also given to us as theta, which is at a distance equal to L, is released. It comes down, it rolls horizontally, and it will be hitting the block. We are given the coefficient of friction, and we are also given the coefficient of restitution, and we are required to determine as what is the energy lost in the impact, energy loss in impact, and then distance travelled by this block. Distance travelled by the block. Now again the problem will consist of, first of all, change in potential energy. When we try to solve this problem, it is going to be the change in potential energy is equal to gain in kinetic energy. So we can very well determine what is the velocity of this mass small m just before the impact. This principle we very well know. Then using coefficient of restitution, using momentum conservation and E, we can find velocity of block. Also, loss of energy in the impact is equal to initial kinetic energy minus final kinetic energy. So even that loss can be straight away calculated. The third part that is asked is the distance travelled. So we can say that loss of kinetic energy of the block is equal to work done over friction, and work done over friction will be the frictional force into distance covered, and this is going to be 1/2 capital M into V square. We can very well determine D. So a problem can be solved using the energy principle, though it is a combination with momentum and the other parts. Another problem will be related to the motion of the block which is attached to another block which is freely hung. Something in this manner. This is mass m1, this is mass m2, and we are given that m1 is moving down, m1 is moving down with some velocity v, with some velocity v. We are also given the coefficient of friction. We are also given the coefficient of friction, and we are required to determine the tension in the particular string. Again we have mass m which is moving with velocity v. m2 also will be moving with the same velocity, but it is going to overcome the frictional force. So if we just pull it with some velocity, then due to that velocity mass m2 will start moving towards left, but after some time this velocity is going to be resisted due to the frictional force which is acting over here, and is likely to come to rest after some time. And so the kinetic energy which we are imparting to mass m1, that will be, that particular kinetic energy, that will be lost fully, plus the potential energy loss which this particular mass m1 will be gaining. There is going to be change in the height also. So there is loss of kinetic energy, loss of potential energy, and both the energies, these two energies will be lost in overcoming the frictional force. But when we talk of loss of kinetic energy, that loss of kinetic energy will be loss of kinetic energy of m2 as well as m1. Loss of potential energy will be only of mass m1 and will be used to overcome the frictional force which is only due to m2. Again the problem of the energy principle to be tackled very carefully. So with these few problems, we will switch over to another topic. We will switch over to another topic that we are required to discuss, and is called as the curvilinear motion. Now the curvilinear motion is the one where the body is going to trace some curve. The body is going to trace some curve, and then we know that when the body is moving along a curve, some body is moving along the curve, the velocity is always going to be the tangential one, velocity v. And suppose the radius is r. Then we can determine the centripetal force which is acting on it, and that force will be equal to mass into v square upon r. And so the acceleration, centripetal acceleration, can also be calculated as v square upon r. So if we can determine that acceleration, the radius of curvature can be very well determined. Now this is one part, and the second part that we have studied earlier in 12th standard or so, that when the body is supposed to take some curve, when the body is supposed to take some curve, suppose this is a vehicle which is moving towards left, then the road should be given some banking. So this is angle of banking angle. Now there is going to be the force which should be acting along the plane, which is responsible for keeping the vehicle on the track, and this is the component which is perpendicular to the road. Of course, the weight of this particular vehicle is going to act in the downward direction, and we will get the components as W cos alpha and W sin alpha. We will get the components as W cos alpha and W sin alpha. Now this W sin alpha component of the weight will be responsible for keeping the vehicle on the particular track when it is taking the left turn. If this component is more, it is likely to overturn. In this particular case, it will topple. So there should not be heavy banking, but there should not be the banking which is so less that due to the centripetal force it will be thrown away, that is out of the curve. When you try to take the curve, negotiate the curve, it is likely that the driver may lose the control and the vehicle will just move in the tangential direction, or it will be moved away from that particular center point about which the track is to be traced. The vehicle might go away, and to stop this particular movement we are applying the component of the force which is W sin alpha, and the component of the centripetal is going to act in this manner, which is m into v square upon r. So equating these two, we can determine actually the angle alpha. And so even on the highways you will be always finding the information about the banking of the road. When you are negotiating the turn, it will be always having the slope in the direction in which you want to take the turn. So this particular vehicle, if it is going inside, it is negotiating the left turn. So even the problems related to this and finding the radius of curvature will also come into picture. It will all depend with which velocity you can take the curve, because this component is going to be the fixed one. It is dependent on angle alpha. Now if you go on increasing the velocity, then it is likely that this component will be more powerful and the vehicle will lose the track. And that's why even in ghats or even while negotiating the curved roads, it will be always mentioned as what is the speed limit. And this speed limit is specifically talking about the velocity with which we can travel along that particular curve, so that we can still stay on the road. Otherwise, if you exceed this limit, then the vehicle is likely to be moving away from that particular track. So these are all the considerations which will work in the direction of the energy principle and are readily used in the real world.